All right. Hello, everyone. Thank you for joining our Tech Talk this Friday. I am Regina here at the Tech Academy. And if you don't know, we're actually a technology school and we have different boot camps that we offer. And I can leave the link in the comment section, but it's at learncodinganywhere.com if you're interested. And today we actually have Phil Scott, who's actually a software developer, and he just told me he's been working in the field for over 15 years. So he's going to give us an awesome presentation on blockchain, and thank you for being here, and go ahead and take it away.
Sure. Thank you very much. My name is Philip Scott. I currently work as a senior lead engineer at Gap, like the clothing conglomerate. Before that, I actually worked at a bank, and I had to deal with blockchains there with some of the digital currencies. And before that, I worked at Walmart on their payment processing APIs and also had to deal with the blockchain mentality as far as security and everything goes there as well. So if you've ever purchased anything at Walmart, you're actually using code that I wrote. In store, online, or in the app, doesn't matter. But that's kind of my relevant background for talking about blockchains. I am by no means a subject matter expert in cryptocurrencies or really even blockchains, but I have implemented and used multiple of them over the years. You can contact me on Twitter, LinkedIn, or my blog that you see here on screen if you need anything else. The code we'll be going over today, again, will be publicly available, so you can reach out and get that from me if you want to pull it down, experiment with it, and run it. There's a small README with the 2 commands you need to get up and running. All right, let's get moving. So blockchains. The goal of this talk is to not introduce you to cryptocurrencies. Cryptocurrencies are, in fact, different than a blockchain implementation. Blockchain is actually just a piece of technology that has been around for quite some time. In fact, even before cryptocurrencies. I'm sure that's not too surprising for a lot of people. It just so happens that it fits the use case for a digitally secure currency quite well, and thus was the technology chosen to implement it with. But today we are going to be focusing really just on the very core technical aspects of like, what does it look like to code a blockchain? And it turns out, to represent that, it's actually not too crazy. So the first question is, what is a blockchain as a technology? You can feel free to, if you have answers, feel free to put them in the chat, or you can raise your hand on mute and give me an answer if you care to. If not, I'll break it down. All right. So blockchain as a technology really is actually just a huge list of items, and each one of these items has a particular identifier with it, normally known as a hash, that is specific to that block. Not only specific to that block, but it's specific to the literal exact moment that block was created. So these hashes are considered statistically unique enough to be reliable, because time, as far as programming goes, is only a forward motion that does not repeat. Right, so the year always changes, days and months may repeat, but that year always makes it a unique moment in time. So the technical description, if you look it up for what a blockchain is it's a public ledger, right? So it's a ledger that technically anyone can access. So in this case, what we normally know this to be is like a cryptocurrency, right? Anyone can mine Bitcoin, anyone can move Bitcoin around, they can generate it. But it is just a ledger that is close to cryptographically infallible as we can get it, right? So basically just a big chain of things that we want to always be able to say, this is a valid chain of things. We know that everything in this chain belongs. And we do that through a couple of different methods, but that hash is the most important identifier. It maintains a continuously growing list of records, in this case, blocks. So there is no theoretical limit to a blockchain. It can just continue to grow and grow and grow. What limits a blockchain's potential is something, the cryptographic strategy for determining what the unique hash of that block is, right? So the computational power required to come up with a unique hash to represent this block. We'll get more into that in a little bit. They're chained together securely by a common cryptography. So this again goes back to that hash. So the way a blockchain works is you have the very first block and it has a hash. Well, the next block in that chain is going to have a reference to the previous block's hash. This is part of how we know where things belong in this chain. And the important part is that we can prove that the next block in the chain belongs or came from or is generated with knowledge of the previous block. This is the fundamental concept of what makes blockchain as a technology secure, is because it allows us to use these hashes, these unique identifiers in blocks to determine whether something does in fact belong inside of this chain. You can think of it as if I have a metal chain, but then I replace one of the links with something plastic. You should be able to tell that that link is plastic. It doesn't belong in the chain. So basically this cryptographic method, which is a big word, it's not that scary, and we'll see some examples of it, to prove that everything it's linked to is in fact metal instead of plastic or something else, is a fair analogy. So what makes blockchain secure? Touched on that just a little bit, right? It's the cryptographic differences between these blocks that refer to the previous block that allow us to identify a block and whether it belongs within this chain. Is it plastic or is it metal? This is a very simplified representation of what a blockchain looks like, really as a whole. So block one, also known normally as a genesis block, so it's the first one that will ever be created inside of your chain. It's the starting link. Normally has a hash, unique hash, and that's because we want to know whether we're at the top of the chain or not, right? We want to know if it's the last link in our chain. All other blocks inside of our blockchain come from the genesis block. It is the fundamental capstone or foundation of what makes a chain, right? Because you have to be able to start it somewhere. We will generate our own genesis block in code here in just a minute. Everything past that genesis block has to have a reference to its previous block. And this, how you get that previous block is dictated how the blockchain itself was implemented. So I'm going to keep going back to cryptocurrency because it's kind of what people know, or at least are familiar with. You have to be able to say, if I want to add a new block to this chain, I need to know what the latest block was. And this is the second part of what makes blockchain secure. Every block or every chain, instance of this chain knows about every block inside of it. And this is called a distributed pattern. So the thing about blocks is that they're self-contained. So you can save the state of a block that has that unique hash, kind of like you're freeze drying something, and then you can rehydrate it and prove that it belongs to this chain. This is what makes blockchain secure, is because you can remove a link entirely from this ledger, and then you can rehydrate it and prove it belongs to this chain. This is the concept behind cryptocurrency ledgers, right? The USB sticks that you plug into the machine that you put your cryptocurrency on. You are removing your blocks from the chain and putting them on a device. The hashes we see here will be really small today because it's proof of concept. But these hashes take tons of time, computational time, to generate, because every cryptocurrency and every blockchain has a specific requirement known as a proof of work that must be met to belong to this chain. And we'll see our proof of work here in a moment. But those ledgers, you can take this link out and put it in a box, re-put the chain, put the chain back together, and then when you want to make the chain longer again, you can take that link out and put it back in the chain and prove that it belongs in this chain. Hopefully this will make a little more sense when we look at some code. So I'm going to stop there because that's a pretty large swath of information. And if you have a question, put it in the chat, or of course you can unmute and ask. Just be polite. All right, let's see. Yes, chains are just hash blocks linked together, correct. But the key important part is you need that genesis block. It has to start somewhere because you have to be able to prove its origin and prove that it belongs to the same chain. We will not be covering proof of stake currently in this talk because we want to focus solely on the technological implementation of what it means to be a blockchain. Not that proof of stake is entirely separated from that, but currently we will only be covering proof of work because that is the cryptographic significant part of a blockchain. Anyone else? All right. So we've seen the physical or the visualization of a blockchain. This talk, I've tried to boil it down. It's a complex subject that can take a lot of time to cover, but I've tried to boil this down in some code to some very fundamental pieces of what a blockchain implementation would look like and how it functions technologically. So I'm going to now share my IDE and we're going to look at some code. We're going to, run some things. Pardon me as I load this up. All right. You should be seeing my IDE now, if anyone can confirm.
Yep.
Perfect. Otherwise, I'm just going to start talking like an idiot, and you're all going to be looking at nothing. All right, so this is a blockchain project that I've written and put together. Just for us to go over, and this is the code that will be available online that you can contact me for. So we're going to walk through just the starting file to see what we want to do with our blockchain, to see what's going to happen. These are just some dependencies. One's for logger, one's for fake name generation. The language we're using, by the way, is Node.js. Can I zoom in? Yes. How does that look? Perfect. Awesome. So I boiled this down, hopefully to something consumable. We only have two files to cover. One's the blockchain and one is the block. An important differentiation here is in something like a cryptocurrency setup, your blockchain is normally like a server and your block is normally a client. And that gets into, again, more of the cryptocurrency setups, like how you mine and generate Bitcoin and things like that. But I'll cover more on that in a little bit. So we are going to create our blockchain. I've done this in an object-oriented method to hopefully make it a little more consumable, to represent everything as their own objects. So we're just going to create a new blockchain. We're going to inform you that, hey, mining has started. We're going to start creating some blocks. And then we're just going to log out some info, say, hey, we've started on block 1. We're going to generate block 1 and say when it's done. And we're going to do this for 2 blocks. And then we're just going to print out the resulting chain, our actual blockchain. We'll print that out. We'll see all the hashes and we'll see all the references. So to start with, let's go take a look at blockchain. So blockchain isn't super wild. The implementation itself is pretty easy. The first thing we need to do is, like any object, we need to construct it. It needs to have initial values, right? It needs to know things about itself. So the actual blockchain in this instance is actually just an array. Now, in a larger implementation, this could be a database, because if something goes up and down, we want to retain the information about our blockchain. It's going to be an ephemeral array for us, so it'll go away as soon as our program is done. Difficulty. This has to do with proof of work. So the difficulty in this case is just a number. It's 6, and we'll see what that 6 really represents here in a minute. But this difficulty could potentially be anything that could represent a numerical value, or even potentially just a computational process. And that dictates how much computational power will be needed to generate a hash that is sufficient and satisfies the proof of work that the block provides to prove that it's part of this chain. Our criteria for proving you're part of a chain isn't something spectacular. It's just how many zeros our hash begins with. That's our only dictation. But in a real life situation, it would be significantly more complex for what we need to generate for proof of belonging to this chain. So you can see that we have start Genesis block here. So we talked about the Genesis block. We know that it's the first block that belongs to our chain. It's the first link. And we generate one in our array of blocks as the first one. So it's the Genesis one. Now what this actually does is we pull our block class in because our blockchain needs to be able to generate and verify blocks. So we pulled that class in, we've created a new one. And what these values are, pardon me, we can see here in the signature that first parameter is the index of the block. Well, it's the Genesis block, so it's going to be the first index, 0. The second parameter is the timestamp. That timestamp may look a little weird, but that timestamp is actually epoch time, which is the amount of milliseconds since the first Unix machine was started. It's a very common way and very easy way for us to keep track of time because it is just an integer. You can do a lot of fun things with that, but that's not what this talk is about. Data. So data in this case is just a string. However, this data that goes along with the block, this is where you would store information about transactions. So this data, if you were implementing something like a currency, this is where all of the data would sit about this transaction. And like who it was going to, where it was coming from, previous block hashes, anything that your chain implementation requires to identify what this block represents. That's where it will go. And then equally as important, the last parameter is the preceding hash. So this, when we generate new blocks, this parameter is what will be set as basically the previous link in our chain. This value has to be set because this is how we validate whether our block belongs in our chain. So if we refer back to the image that we were looking at where the previous hash was always referred to by the next block, this is that value. Here it's just 0 because it's the Genesis block. Nothing really generated it, but everything has to sit on top of this block. So it's a lot of talking, I know. We'll see it all run here in just a couple minutes. We have a couple more methods here. Obtain last block is exactly what we think it is. We're just getting the last known block that was added to the chain. And that's what we use to get all of the information about that last block, so we can generate a new block off of it. Add new block. So this is relatively simple for what we need here. And you can see that we use get last block, we pull the hash out. This is our preceding hash that we're going to pass to the new block we want to make. But then we see proof of work, and we see that this difficulty has been passed into it. Well, we know our difficulty is 6, but what does it mean to prove your work? Let's actually jump into block real quick. Block is super small because, again, these are really just containers for data that have, a big long hash tied to them and whatever data you attached to it. And we can see everything we passed in from the previous class: index, timestamp, the data, preceding hash is all here. The signatures match. But proof of work, it takes our difficulty. And then really what we're checking is our proof of work for this chain implementation is every block, its hash must start with the number of zeros equal to difficulty. Now, this is important because this is where the computational cycles go for mining a block. So the work to be done, like why people always get these, real intense CPUs and GPUs and everything to mine Bitcoin and everything, this proof of work is essentially what they're emulating when they do that. They're going through this computational process to basically take their random chance at generating a hash that meets the requirements. And that's something that I think gets lost a little on the technical side. Your chance of mining a cryptocurrency is literally random chance. You are attempting to generate a valid hash based on a requirement that you don't have power over, which means it could technically be anything. So your chances of generating one of these valid hashes could be in the hundreds, it could be in the billions, it could be in the trillions, depending on how big you get, you could well be in with a Googleplex of times you would need to recalculate to see if you can get one of these hashes. For us, we're just going to be generating a random hash, checking if it has the difficulty zeros, right? So 6 zeros in the beginning. And if it doesn't, generate another hash, check it again. This is the proof of work. Now, this is a very simple proof of work once again, but we're going to run this and we're going to actually see how long this takes, because it doesn't sound like a lot. 6 zeros, surely we can generate 6 zeros. I have one test run that took 10 minutes to generate 2 blocks with 6 zeros. Like the amount of computational cycles to get that is actually pretty significantly more than you might think. Let's talk about this right here, nuance. So this small value that really only exists inside of the block gets iterated every time we fail to generate a proof of work. This is part of why it's kind of just a random chance of you generating a SHA that's valid. Because we're going to take a look and compute hash. So this is actually what generates our unique hash to represent this block. You'll notice we take a bunch of properties like the index, the preceding hash. So this is how we can validate that this block belongs to this chain, because we can recalculate its hash with all of its properties, because it saves the timestamp of when it was made, and we know the preceding hash, and we have all the other data attached to the block. We can recalculate this block's hash based on the previous block's hash. This is the fundamental crux of what blockchain does to secure and know what blocks belong to its chain and don't. And this hash, while I just used a 256 here, a SHA, this is dictated by whatever, again, with cryptocurrencies, whatever cryptocurrency you're footing into, right? They dictate how this is calculated, and you get the client that knows how this is calculated. But you have no idea what your success chance is of actually generating a hash that's valid. But once you do get one that's valid, it's always provable to be valid up the chain. So it's a lot of words. So that's a lot of talking. Are there questions so far? I see. Where are these iterators? The language is Node.js. The iterators methods. So there is no library. These are just two classes that I wrote, and this is why blockchain was so easily adoptable, right? I have no libraries in here to make this blockchain work. This is literally just two raw classes. This is a fundamental structure, much like a linked list or a queue. They can be implemented without any libraries. And you can go, again, I'm happy to give the code out for this. It's public on GitLab, happy to hand it out. But there are no crypto libraries that I'm using here. The only libraries I'm using are for logging, random data generation, and the SHA, the crypto library for my 256 SHA. In Node.js, there is in fact a crypto library that you can use SHA 256 without a doubt. I brought it in here with Crypto.js. Crypto.js, I'm going to go off on a tangent. Crypto.js is just faster than the native module. That's why I used it here. It's just speed, which is important when you're generating different blocks because it's slow. Any other questions before we move forward, see some running examples, and go over how do we validate our chain? All right. Well, then I guess we'll move on. One of the obviously important steps to a blockchain is the chain has to be able to validate whether the block it was given belongs to it, right? Is it valid? And once again, this is kind of the crux of a cryptocurrency, because there's a severe issue with cryptocurrency, fraud, where because these are just pieces of data with a unique hash, if that hash calculatory method is ever divulged, potentially I can falsify a block with a quote-unquote valid hash that could technically be accepted. But once it goes into validation, they'll be able to know that it's not actually part of the real chain. And that's a very interesting note that I'm going to bring back up at the end of this when we talk a little more in depth about the consequences of cryptocurrency and how these affect it. So our blockchain knows about all of our blocks. So when we run check chain validity, it's going to loop through all of our blocks. And what this does is it gets the preceding block that the actual chain knows of. So the idea is that we don't ask the actual block about anything. We're just going to take information from the block and actually attempt to recalculate and validate that block's information by recalculating the hash. So we can see that we get our current block. We get the previous block because, again, to validate a block, we need to know the hash of the previous block in the chain. And then we say, great, we have all of our information. I'm going to ask my current block that I'm checking to recompute its hash. Well, if it doesn't recompute to what the chain knows that hash is, the validity fails, right? If that block can't regenerate the same hash with its current data, we know it's bunk, it's no good. And it doesn't belong in our chain. And here we just return false, right? Just get rid of it. But also, we check for if the preceding hash is unequal to the preceding block hash. So if the hash that the block we're currently inspecting, if its preceding hash does not match the preceding block's hash that we know it should have, it's also bust. It doesn't belong in our chain. And this check is to protect you against things, again, like the fraudulent blocks, right? Because technically this could calculate if it's fraudulent, but if they don't have the preceding hash in there and it doesn't calculate, then it will be bust again. If all of those checks are good, we can return true and say, yes, our chain is valid. All of the blocks in our chain are good to go, and they were generated using this chain and belong to it. So that is actually all of the code for a blockchain. We have fundamentally created a blockchain. Let's actually go see it run, though. For the sake of time, I'm going to lower the computational complexity to 4 zeros. So let's actually go see this thing run. So we're going to sit here and it's going to start cranking through things. So again, that was super fast, but our complexity for calculation is also very low. We only require 4 zeros, but let's go inspect some of this. So this is our Genesis block, and there's a couple important things to note here. One, our knowance is 0 because we never attempted to recalculate the Genesis block because it's the first block, right? If the Genesis block is happening to regenerate multiple times, something is very fundamentally wrong with our calculatory process and how we create a Genesis block. Something also to notice is the hash here. So we said our requirement was, our difficulty was these hashes have to start with 4 zeros. That was the complexity we set. But notice the hash of the Genesis block, in fact, does not start with 4 zeros. This is another indicator that this is a Genesis block. Generally, your Genesis block will not conform in some cases to your difficulty, and that is part and like a red flag for if you do get a Genesis block. It's probably a fraud, actually, that someone is trying to put in there if it does match the other difficulties that your other blocks have been generated with. Again, our preceding hash is 0, right, because it's Genesis. And we can see the timestamp, the data that we put in there in its index. The more interesting part is the next, our actual blocks that we make, right? So we made 2 blocks. We can see the index is 1, and the data, pardon me, I tried to make it a little more real world in this particular instance. So sender, recipient, and quantity. This is representative of what we do in the banking space, right? We have a blockchain for, it can actually get pretty interesting. So every account at the bank I worked at actually had its own chain. And that chain, so like when you go look at your transactions in your report for your bank, right? You know, I've spent too much on coffee this month, and you're looking at that. Those transactions for the bank I worked at, that was actually a blockchain. So every customer was, in fact, their own blockchain. And that's for a lot of reasons, mostly laws. Turns out the feds are real on top of that. But we can see that we sent it, and we can see the preceding hash, again, does not start with 4 zeros, so we know it's the Genesis block. But we can see that the hash for this block does, in fact, start with 4 zeros. But even more interesting is it took us 62,962 hash creations to get that one hash that started with 4 zeros. Which does not sound like a whole lot, but potentially, like with a SHA-256, we have a mathematical chance is decreased by almost 18% per extra zero that we put in there. And that creates an exponential rise in the amount of computational power required to find a hash that starts with, say, 6 zeros. I actually pre-ran a 6-0 run for you that we'll take a look at. The next block is much of the same, right? We can see that its proof of work is valid. It starts with 4 zeros. And we can see its preceding hash is, in fact, the last block that was created. And an interesting note here is both the nuance and the timestamp affect what hashes get generated. And you'll notice that it took us a really long time to find that first hash. But because our previous hash is used in creating the next hash in the chain, it should take, in theory, less time based on the timestamp to find a new hash. And in fact, it did. It only took us 5,701 hash generations to find the next hash that started with 4 zeros. A small note on like time and how we deal with time in programming. This is where this becomes relevant, right? Because timestamps will never repeat, which means we have nearly like a 99.9% chance of always getting a very unique hash. So sometimes it'll take us 5,000. Sometimes it'll take us 100,000 tries. This is what I was talking about when it's really just random chance for you to actually mine a block, is because really the requirements for these hashes are arbitrary. It's whoever designed that blockchain's choice. So they can make it super easy. They can make it ludicrously hard. And that's a pretty gross oversimplification in the case of like cryptocurrencies and stuff like that. But and we can see the difficulty was 4. All right. So we ran it. We broke it down. We'll do another round of questions. I see zooming out. What is this code doing? Well, we were looking at terminal output. But this is the code we just ran using the 2 objects we created, blockchain and block. And all we're doing is adding a new block twice and logging out the results of those blocks. Alec, I don't know if that answers your question. I may have been on different code when you asked that. The preceding, so that was in our proof of work. So we can see that the question was, which piece of code is making sure the hash has 4 preceding zeros? That happens in proof of work. So the difficulty gets passed in, and the difficulty is dictated by the blockchain, as it should be. A block should not be able to dictate its own success. So that gets called here, proof of work, difficulty, right here. And difficulty is currently set to 4 inside of our blockchain. Then when we call add new block, this gets called. It takes the new block. It sets the block up to calculate its new hash. It calls proof of work, passes in the difficulty. That difficulty is then used in this right here. So it looks for the preceding digits. And then if it does not find those preceding 4 or difficulty X digits, right, it will compute another hash until it finds one. And this is all within a while loop. Hopefully that answers your question as to where those preceding zeros come from. All right, so let's go take a look at this guy right here. So this is the result of a difficulty 6 run. So really it sounds super simple, right? We just want 2 more zeros to be at the beginning of our hashes that we generate. But I would like to point out the significant difference in time between our 4-0 run and our 6-0 run. As we can see, we started at 2103 right here to start generating our first block. And that took about roughly 1 minute. However, past that, we started generating number 2, which started at 4 minutes. but ended at 11 minutes. So by just requesting 2 more zeros, we more than tripled the amount of time required. It's doubling up on me. I'm not sure why. The amount required from our 4, well, actually more, because you can see when we wanted 4, it actually ended. It was almost instantaneous. So this is where the calculatory power, quote unquote, mining, the difficulty of that is dictated. Now, we can start talking about cryptocurrency a little more now that we kind of have a core understanding of what a blockchain is. Which actually, I don't know. How are we on time?
We still have 15 minutes left, but we can also, this usually takes like an hour, but sometimes we go over, which is fine.
Okay, great.
No worries.
I just want to make sure I'm not wasting anyone's time.
No.
So within the context of cryptocurrency, with this current implementation, we can kind of start to wrap our head around what actually, what's the function of a blockchain and how does it work? This, of course, is not a distributed blockchain because we don't have a server and a client that are communicating and validating each other. But there is one point I wanted to hit on, and that's around checking the validity of a chain. So when within the context of a cryptocurrency, and this is for Bitcoin in specific, some other chains have some different implementations. But the way you mine Bitcoin is you're not actually mining the hashes, basically, yourself. What happens is what their client does is all your processing power is actually checking how valid other blocks are. So if you're mining Bitcoin, really what you're doing is they have essentially turned the internet into its own big supercomputer. So every time you start mining Bitcoin, you're running their client, you aren't generating these hashes, you are doing all of the calculations required to validate a block belongs to the chain. And after you have validated 1 megabytes worth of information, or checked whether 1 megabyte versus of block data that has been validated or not, you send that to the Bitcoin server and say, hey, I've done this work. I've validated or not validated whatever these 20 blocks that you gave me to check. Then what happens is the blockchain attempts to generate you a hash that has the potential to represent and be valid. And in this case, you would get a block or a coin in this case. And that's a very fundamental misunderstanding I find a lot is you are not, when you're mining Bitcoin, you are not actually generating these hashes. All you're doing is checking you're validating that all of these transactions with the coin are valid. You're recalculating all of these hashes for Bitcoin. And once you've done that work, you ship off that package with all your validation checks, and they say, okay, great, you've done that. Let me try to generate you a hash. And then it says, well, sorry, it wasn't valid this time. So now you go mine another 1 megabyte, or you do another 1 megabyte of validation, and you continue to do that. And that's actually what mining a coin is in this case. You aren't actually generating the coin. The blockchain is generating the coin. You're just doing work in exchange for basically the raffle ticket to say, do I get a valid hash? Do I get a currency or a block back? All right, that's really about all I have. So it's all questions. Feel free to put them in chat, raise your hand, ask them yourself. Oh, come on, I don't think I'm that good. Surely there's questions. How is the hash generated? So the hash in this particular case is generated via a SHA-256 hashing algorithm, which is pretty standard fare these days for most irreversible hashes. Though that will change dramatically in a real implementation, right? A blockchain. Can I zoom up the code? Yes. This hash can be calculated a majority of ways. Most cryptocurrencies actually write their own cryptographic strategy for generating these hashes, which is kind of what makes them unique, right? Because if every cryptocurrency was using SHA-256, well, that means I could just sit here and generate SHA-256 hashes all day and send them to every cryptocurrency possible. And chances are I could probably get some valid blocks out of that. So that didn't really work too well. So this compute hash will be dictated by whoever writes the blockchain, or in this case, whoever wrote the cryptography for the coin. Not covering smart contracts today because this is about blockchain, not cryptocurrency. So Jeffrey, it's the way mining works. You are not mining the hash. The blockchain gives you a hash after you validate 1 megabyte worth of blocks. So you're exchanging your CPU power for a raffle ticket for the blockchain to attempt to generate you a hash that is valid, and you just kind of do that until you win, basically, and you get a block. Is JS the best for blockchain? No, not at least not in my opinion. Node.js, I love it. Don't get me wrong; it's very good at what it does. However, cryptography is a very intensive process, and Node.js is a single-threaded language by nature, which is not good for long-time computations. So I would say something more along the lines of like C++, even some Rust, would be much more preferable for if you like to build a blockchain at scale that's actually going to get used within the context of a cryptocurrency. Can Node function just fine with a cryptocurrency? Yes, and in fact, the services at the bank that I worked at, all of our services were written in Node, and all of our blockchain implementation was also in Node, but it had a fundamentally different use case than a cryptocurrency. We used it only as a ledger, and we only had to validate it when something potentially went wrong, like fraud. And we had like specific servers and runners for those jobs because we know they're big and they take a long time. The link to the code repository, I will actually just throw that in chat now for people that would like it. There we go. So that's where all the code is. All the code we just ran is up there. You can pull it down. You can install all the utilities. You can run it. It's super small. And of course, feel free to reach out with questions if you're running it, experimenting with it. Anyone else?
All right.
All right.
Looks like there are no more questions, but I did link his LinkedIn. So if you have any questions, feel free to reach out. We're also going to be, this is a recording. So I'm going to post it later in our Tech Talk playlist on YouTube. So if you want to rewatch this, here is the link for that. Also, we do have another Tech Talk coming up next Friday, and it's going to be about how to succeed as a software developer. So if you're interested in that, here is the meetup link for that. You can go ahead and RSVP. But yeah, thank you so much for being here, Phil. That was an awesome presentation.